Sure. Just let me. Good afternoon, all. I welcome you here, the Astronomical Society of India meeting, first day afternoon session on Extragalactic Astronomy. And we have 5 speakers today. The first speaker will be speaking for about 30 minutes, followed by some 4 talks of 15 minutes each. And each speaker will be told 5 minutes prior to their allocated
of gaseous disks as a powerful probe of galaxy formation and evolution. So this is a brief plan of my talk. So I'll start with a brief introduction and motivation. I will discuss what are the challenges in the field, and to overcome those challenges, I will employ the hydrostatic modeling of the to model the galaxy disk, and give you some applications where we really apply this technique or this modeling to probe galaxy formation and evolution process or the physics. Okay. So what is the structure of a galaxy? I mean, structure by structure, I mean the density distribution of different components. Okay. So in the right hand side here, I'm showing a face-on galaxy which depicts the radial distribution of density. That's the radial structure. And in the left hand side, I have shown a galaxy NGC 891, which is an age-on galaxy. So here you can see or try to get that what is the vertical structure of the baryonic disk, which is luminous of the galaxy, right? So this is what we are looking for, and I will give you like what we are actually trying to look and why. So why particularly vertical structures are important? They are important for many reasons. First of all, that they help us to understand the stability of the disk. For example, if you know the vertical structure of a disk at any point, so you would be able to understand or calculate that how stable is the disk would be against external perturbation, for that matter, right? So that is one important aspect which is crucial in terms of dynamical evolution of galaxies and in terms of star formation as well. Then the second aspect is that how effective the stellar feedback processes would be in terms of polluting the circumgalactic medium or the intergalactic medium which surrounds a galaxy. So here I have shown a cartoon picture of galaxy ecosystem. So as you can see, there are a lot of stars in the mid plane, and there would be a lot of energetic activity, for that matter, stellar feedback processes, supernova explosion and stellar winds and so on. So these processes would eject metal enriched gas into the into their vicinities, right? So now if the vertical structure or the the gas disk is thick and they are very kind of resistant, so then this metal enriched gas will not be as effectively can escape from the mid plane to the circumgalactic medium. So in that sense, if you want to know that if I have an ecosystem of galaxies, some dwarf galaxies and spiral galaxies, and you know that how much metal they are producing over the time, but you also need to know that what is the distribution of their gas disk in the vertical direction, so that they will be effective. I mean, they can effectively mix this metal enriched gas into the circumgalactic medium or intergalactic medium. So in that sense, it is also important. Then another important aspect is that the effective absorption cross section towards high redshift bright quasars. Okay. So say for example, I have a galaxy over here and I have a background bright source over here. Now this galaxy, how much effective cross section it will offer for absorption, that would depend largely on the thickness of the disk of the galaxy, right? So if I have a very thin disk, then yes, it also depends on orientation, but it also matters that how much, if it is like oriented in age-on condition, then the thickness of the disk actually matters a lot, specifically in the high column density regime like DLA. So there, because it's very difficult to produce high column density if the galaxy is face on. So in those cases where we have high column density absorbers, So there it is very important to know what is the thickness of the disk to understand that how much effective cross section it will produce. And this has a significant implication in understanding, cosmological evolution of galaxies, for that matter, to determine that how many galaxies are there at high redshift per unit volume, right? So in that sense, it is important to know what is the thickness or the density distribution of gas in galaxies. And one of the most important and my favorite aspect is related to star formation, right? So what people have, the traditional wisdom was that, the gas and the gas surface density and the star formation rate density, so they are found to be correlated observationally. So this is basically the famous Kennicotte-Smith law. So basically you have in x-axis the surface density of gas, and in the y-axis you have surface density of star formation, right? So people have found that they are correlated, the surface density of gas and the surface density of star formation rate. But recent study, what they have found is that more than these surface densities, volume densities are actually more correlated with much less scattered, and the agreement is across the board for different types of galaxies and different types of surface density values, from low density to high density. So, and this has been done by Bacchini et al. Very recently, and for a limited number of galaxies with large number of, reasonable number of assumptions. And they have concluded that the volume densities are actually much more fundamental than surface densities, which actually also easy to understand, in a sense that the star formation would in a volume would depend on the total density. But because we cannot measure this volume density so accurately observationally, people have relied on these numerical, these empirical relations, right? So in that aspect, if you really want to understand that how star formation will proceed in a galaxy, so you really need to get into the volume density instead of surface density. So that will give you the complete picture, right? So molecular gas in particular is actually important. Okay, of course, atomic gas is very much important. So atomic gas and the molecular gas, these are the two primary component of the molecular disk. Atomic gas provides fuel for star formation. It's a long-term fuel, but star's immediate fuel is molecular gas. Okay, so the molecular gas is the primary fuel for star formation, and it accounts almost half of the interstellar medium. And it regulates it largely regulates galaxy formation process, because if you see dwarf galaxy and a spiral galaxy, you will find that depending on that how much molecular gas content in different types of galaxy, their evolutionary path will be completely different. So in that aspect, molecular gas is quite important, and estimating the three-dimensional distribution of molecular gas in galaxies is quite important. So what people have tried is that if it is important to estimate the molecular gas distribution, three-dimensional distribution of molecular gas. So let us go and try to look directly and try to measure if it is possible. But direct measurement is not possible. That is because of line of sight integration effect. So say, for example, I have two cases over here. In the right-hand side, I have a face-on spiral galaxy, right? So here, if I try to probe the density distribution in the vertical direction, because everything is like coming and adding together, I will not be able to tell. So then you might say that, okay, let us go in a case where it is edge on, then the vertical distribution I can see. But there is also a challenge. There is also a problem. Say, for example, in this case, in the left bottom panel, you want to estimate the vertical density distribution over here. But this place, vertical density distribution at this strip, okay, so this strip actually have the emission from all these radiuses, this line. So this is basically, if you just deproject it from the, if you see from the top, so this is basically your line of sight. So this basically collecting the radiation from this point at the far radius, from this point which close to the radius, and like this. So if I have a profile at particular radius, so this is basically will have sum of all sorts of profiles coming from different radius. So effectively what is happening, that all getting summed up, and ultimately what you are getting is a summed up effect. So directly measurement is not possible, and determining the particle density distribution through direct observation is not possible. Okay, so but for for the Milky Way, because we are residing inside the galaxy, some amount of measurement is possible, targeting individual clouds at different L and B, that is, and one would be able to kind of estimate the density distribution. So here what I'm showing is that it is the thickness of the molecular disk as a function of radius for our Milky Way. Okay, so this is basically kind of a measure. This Z hub is basically the scale height, and this is a measure of how thick is your molecular disk, I mean, in our own galaxy, Milky Way. So this is inner radius up to 10 kiloparsec, and what people have seen that this is very small, that is the molecular disk is very thin, between 20 to 60 parsec, and at the outer radius it goes around 100 to 200 parsecs. Okay, so these observations led to the first classical picture of the molecular disk, which says that it is thin disk. Okay, in the inner radius it has like 20 to 75 parsec, in the inner galaxy less than 10 kiloparsec, and it is like 100 to 200 parsec at the outer galaxy. Okay, and this is dynamically decoupled, because decoupled from the atomic gas, because the atomic gas scale height people have found is to be much larger. Okay, so atomic gas disk is much thicker as compared to the molecular disk, which is much thinner. So this was the classical picture, but sensitive observation has changed this idea. For example, Waterloo et al. Used IRAS point source observation and found that at the outer radius, like beyond 10 kiloparsec, the molecular scale height and the atomic scale height, they are actually as per level. They are quite comparable. And this is for our own galaxy, and even for the external galaxy, that Ozone galaxy NGC 891 also, what people have found that molecular gas found to be at distance like from 1 to 1.4 kiloparsec above the midplane. So if the molecular gas, people thought that it would be in a very thin disk, but in the external galaxy in NGC 891, they found that the molecular gas to be at height 1 to 1.5 kiloparsec above the midplane. So which is very surprising, because traditionally thought that molecular gas is like in a cold component, it is very dense component supposed to be at the midplane. Then how this gas can be at that height and how they are surviving, right? So to know or to answer all these things, we really need to know, or we really need to get what is the actual density distribution. So in observation, we said that it is not possible. So let us say if it is possible by theoretically calculating, theoretical estimation is possible, and that is assisted by observation, right? So to do that, what we have done is that we have considered the galaxy, we have modeled the galaxy is a multi-component system, and this is a cartoon picture of the galaxy, cartoon picture of a galaxy disk. In the vertical direction, the pressure will be balanced by gravity, and in the radial direction, the rotation is balanced by gravity. Now we are only focusing on the perpendicular direction, and we are saying that in the perpendicular direction, the system is in vertical hydrostatic equilibrium, and if it is in equilibrium, we will be able to set up the Poisson's equations of hydrostatic equilibrium. Okay, so this is basically the Poisson's equations of hydrostatic equilibrium, and left hand side is basically telling you about the pressure, and this term, that is sigma z, that is the velocity dispersion, is an indicator of how much pressure in each component, and the right hand side is basically the gravity component, which has contribution from all the components: stars, atomic gas, molecular gas, and the dark matter halo. Okay, so now this the solution of this equation will basically give you the vertical density distribution at every radius. So this has been done using 8th order Rangagupta method, and employing a very classic approach, iterative approach, first developed by Chanda and company. And this has turned out to be one of the very powerful tool to investigate the vertical structure. Okay, so we have done, we have kind of employed this technique to solve the vertical structure here, in this case in the molecular disk. to find out the vertical density distribution of molecular gas in galaxies. So first galaxy we have tried is NGC 7331. So this is a very interesting galaxy. This is called this galaxy is called Milky Way's twin, and we have used the data from Things and Heracle survey to solve the hydrostatic equilibrium equation and get the vertical density distribution of molecular gas, right? So this is kind of a typical solution of the hydrostatic equilibrium equation for NGC 7331 at R equal to 6 kPa. So this is kind of Z is basically the vertical height from the midplane. So the stellar density falls off like this. This black curve is the molecular density, and this is the H1. Now if I can solve this equation, I can solve this equation at every radius, right? Now if I solve this equation at every radius, and I am getting the density as a function of Z and solving at every radius, so effectively I am getting the full idea of the density distribution in that galaxy, right? So at every radius and at every Z. So this gives a complete picture of the three-dimensional distribution of molecular gas in NGC 7331. So what we can do with that? So we can build a 3D model of the this density distribution and then incline this model to the observed inclination, project it into the sky plane, and convolve with the telescope beam, right? So I have this three-dimensional density distribution. I incline it to the observed inclination, project it into the sky plane, and convolve with the telescope beam. So that will be exact equivalent of my observation, right? So now, if that is my equivalent observation, I can always go back to my observation and compare these two and ask this question that, okay, I have assumed that this disk is in vertical hydrostatic equilibrium. I have employed the observations to solve this equation. So whether those things are correct or not, and in a way that whether our modeling is correct or not. So to do that, so this is basically the surface column density map what we have got from our model. Now we compare it with our observation, right? So the background, the color scale is basically the observation, and these contours, they are coming from our model, right? So in apparent view, it seems that, okay, they are matching quite well, but we can even investigate in a bit deeper and take the vertical cuts along these lines, which is 2, 3, and 4, 2, 3, 4, and 5 kiloparsecs, and compare the vertical column density profiles. And this is how they look like. So this red and the black curves, so they are basically coming from the observation, and the blue is from our modeling, okay, from our hydrostatic modeling, right? And as you can see that they actually compares pretty well, okay, at different radius. It's not like in one radius. So it kind of giving us confidence that our modeling is correct, and the proposition and the assumption what we have started with, that this is in vertical hydrostatic equilibrium, that is not actually far from the truth. Okay, so now coming back to the original question, that, okay, we have started saying that, okay, whether it is possible to have this thick molecular disk, going up to 1.5 kiloparsec, whether it is possible or not. So to answer that question, now I have this model which matches our observation. So I have inclined this model to 90 degree, that is edge on, and ask this question: if I incline this to 90 degree and project it into the sky plane, can this disk be thick as like 1 kiloparsecs or not? So we have found a very interesting result that this, if you incline it to 90 degree, the scale height at half width at half maxima is kind of around 500 parsec. So this is like half width at half maxima, and if you have a half width of half maxima of 500 parsec, it can easily produce a gas disk which is like 1 to 1.5 kiloparsec thick. Okay, so it means that what people were like assuming that big puzzle, that how the gas can be at so much of height, this is easily explainable assuming the hydrostatic equilibrium. I mean, in hydrostatic equilibrium this happens naturally. Okay, you don't need to there is no kind of surprise in that. So this we have done it for one galaxy, and we asked this question whether this is true for other galaxy, or many other galaxies or not. So to do that, we have done this exercise on 8 other galaxies from Things survey, and we have found consistent result actually. So all these galaxies have shown that, almost all these galaxies have shown that the vertical extent of the molecular gas can be 1 to 1.5 kiloparsec. So there is no problem. So a thick molecular disk. So the conclusion from this part is a thick molecular disk originates quite naturally under the assumption of simple hydrostatic equilibrium. But is it the whole story? No, this is not the whole story. So there is another part to this story, which is by investigating the spectral width in the molecular disk. Okay. So what people have studied is that people have studied individual spectrum from a region, individual molecular spectrum from an individual region. And what they have found, if you look at individual spectrum, the width of the spectrum is actually small. Okay, something like 7 kilometers per second or so. But if you accumulate spectra from different region and stack them by aligning their centers, then this stacked spectra has much more higher signal to noise ratio, and then the width of this stacked spectra is actually much higher. So it is something like around 12 kilometers per second. So now the question is that if I have only one component molecular disk, which is thin disk, and have 7 kilometer width, then it really does not matter how many spectra I add together. Every spectra has like 7 kilometer, 7 kilometer, 7 kilometer, right? So if I add all of them together, so that's supposed to give me 7 kilometer per second width. But what we are getting is 12 kilometer per second. Okay. So this is basically done by Caldupramo and Mogotsi et al. And another observation, single disk and interferometric observation found that in the interferometric observation there has been a substantial amount of gas missing. So here in the left panel and the right panel I am showing the same galaxy, which is M51. Left panel is using single disk iron 30 meter single disk, where the beam size is 22 arc second, and right hand side is from Plateau-Devor interferometer, and which has a resolution of 1 arc second. Now in single disk, it has been found that it is recovering much more flux. Okay, much more flux. So why it can happen? It can only happen that if you have sufficient amount of diffuse gas, which is low density. Okay, so those gas will not be seen in interferometric observation, but they will be picked up in single disk observation. So if we combine all this idea, so then the picture emerges of the molecular disk is this, that you have a thin disk, and along with that you have a thick disk. Thick disk means low density gas, which actually goes much beyond the mid plane, which is actually much puffed up. Okay. Now because this thick disk gas is low density gas, in individual spectra, when you are investigating individual spectra, in that spectra their contribution or their SNR is so low that you don't actually realize them that they are there. Okay, so what width you see in that individual spectra is the width of the thin disk gas component, which is much more dense, right? But when you stack many spectra, then the SNR goes up. Then these low density gas signal coming from this low density gas actually then they piles up, and then the width of these this component also gets into the picture, and the width of this component is much higher than the thin disk component, right? So this is basically the picture then proposed, that the molecular disk has like two components, thin and thick. Thin disk is basically flows to the mid plane, consists of like high density gas having low sigma, low velocity dispersion. Thick disk actually goes much beyond, and they have higher velocity dispersion, and they have low density. They have very low density, right? Now this is kind of the picture which explains the observation, right? So we still do not know, and there are a lot of research going on in this. And the immediate questions comes up after this picture is that how do we test? I mean, of course, it is explaining the observation. Is there any direct observational evidence? Second is that what is the origin? How can you produce this low density molecular gas, and how do they survive at that large heights, right? I mean, if this molecular low density molecular gas is actually quite high up, then there will be a lot of radiation, interstellar radiation, which try to dissociate this gas, right? So how do they survive at this large height? And what is the fractional abundance, that how much gas is in thin disk and how much gas is in thick disk? So in particular, I have addressed this question by the following way, is that, say for example, I have a thin disk which has like, you know, this sigma 7 kilometer per second, and I have a thick disk which has like a sigma of 12 kilometer per second.
Now you have only 5 minutes to go.
Yeah, I will finish it before that. Yeah. So then if I combine these two in a different proportion, say for example, I mix it like 50% thin and 50% thick disk, so then the width will be different, because the width of these two individual components are different, right? So here I am showing an example. If I have 50-50 molecular 50-50 thin disk and thick disk gas, then I will have a width of something like, you know, 9.8 kilometer per second. But if I have like 70% gas in thick disk and 30% gas is in thin disk, then I will have a velocity dispersion of 11.6 kilometer per second. Now these are actually quite different, 9.8 and 11.6, and you know, this width of these stack spectra, so they are actually can be measured observationally, right? So then what I have done is that I have built my model with different proportion. Okay, at every radius I assume that, okay, my fraction could be from 50% to 95%, and at every radius I have changed these fractions, and for every fraction, okay, every type of fraction I have modeled the disk, and I have produced that what should be the velocity dispersion profile, right, which is observed. So this is kind of these blue points, blue curves are representing velocity dispersion profiles, sigma profiles for different thick disk gas fraction, and these stars are basically observed values. So from here we have calculated, which is a very, you know, surprising result, is that we have found almost 70% of the gas, molecular gas, is in thick disk. Okay, and this is done for NGC 6946 Galaxy. So this is quite surprising. So this is for the first time we have, you know, determined this thick disk gas fraction in a resolved manner at 500 parsec resolution, and this kind of, you know, gives a hint about the origin of this thick disk gas, because, you know, people think that propose that, you know, the star formation activity produces this thick disk, means, you know, you have stars at the midplane which is forming, injecting energy into the system, and this high density molecular gas, they are actually coming out because of these processes, and then it is forming like thick disk. So in that sense, if you adopt that proposition, then, you know, because the central region of the galaxy has like much more star formation as compared to the edge, so you would expect that the, you know, relative proportion of thin and thick disk would be thick disk proportion would be much higher at the central region because of the higher star formation. But here you don't see that. So it kind of assists, you know, kind of support a scenario where like the thick disk gas has been, you know, or originated first, and then they over the time coagulated to form the thin disk. So I mean, more research is needed to kind of humbly conclude any of these proposition, but this is kind of a very interesting result. So here is the summary, kind of what we have learned from about the molecular disk in galaxies, and just to give a glimpse like what else can be done with this vertical, you know, solving this vertical structure technique, is that we can actually do a variety of very interesting stuff. For example, to determine the shape of the dark matter halo. So I mean, traditionally people assume that, you know, dark matter is spherical, but if there is a change in shape, or, you know, different shape of dark matter halo exists, like oblate, spherical, or prolate, then the gravity in the vertical direction would be different, and the this vertical scale height profile would be different. So this is done for a dwarf galaxy UGC 4148, and for 3 different types of dark matter halo, you see that this is different, and this can be compared with the observation, right? And to comparing with the observation, one can, you know, kind of conclude that whether, you know, this galaxy has a spherical dark matter halo, or, you know, otherwise, right? This technique also can be used for modified Newtonian to probe other alternative theories to dark matter, like modified Newtonian dynamics, which, solving the hydrostatic equilibrium equation under Mond formalism, one can ask this question whether this is consistent with Mond formalism or not. Okay, so the take-home message is the vertical structure of the gaseous disk can be used as a powerful probe to understand several galaxy physics, as well as fundamental physics like theory of dark matter or alternate gravity theories. So I will stop here and thank you.
Yeah, thank you, Narendra. One quick question could be taken either from online participants or participants among the audience. Online participants, please, if you have any questions.
Yeah, I see Chanda has raised hand.
Yeah.
Yes, Chanda, please go ahead. Yeah. I can't hear.
Yeah, maybe the chat you can definitely reply.
Yeah,
later.
now I think you can hear me.
Yeah, I can hear you. Yeah, Chanda, please go ahead.
Yeah, so I had just two questions. One was the thick disk you said forms first. So what gives rise to the velocity dispersion of molecular gas in that? And secondly, does the Milky Way have a thick molecular disk? Because people haven't, I think, found it so far, though.
Yeah, so this is a very interesting question. Frankly, we do not know actually. I mean, so the thick disk velocity dispersion, people, I mean, propose it this way that they form fast, and whatever the residual dynamical, I mean, they are like in small chunk, very small, tiny bits of pieces. And they have this velocity dispersion, which mostly attributed to the turbulence activity, and also some residual, velocity zigzag from, when the gas actually condenses from all the direction. But this is a proposition. I mean, in a sense that we still do not know, like, what exactly causes this thing and what is the origin of their properties. And to answer your second question, in the Milky Way, it is very hard because we are sitting inside the Milky Way. Even like we are, observing external galaxies, the beam size kind of we have that kind of cover a region of like few kiloparsecs, right? Mm-hmm. And even within that few kiloparsecs, in one beam we cannot detect this this molecular gas. And for if you are sitting inside the Milky Way, the beam size is so small, the amount of signal within a beam is actually too small to kind of conclude this thing way. But I mean, this is an interesting kind of area where people are trying to look with better instrument, for example, ALMA.
Yeah.
Okay, thanks very much, Narendra. Yeah, nice talk.
Lack of time, I think if someone of you have any further question, please do write to Narendra. Thanks, Naren, for your talk.
Thanks.
Second talk, since we are already 3 minutes late by now, it's by Prerana Biswas. She will be talking about revisiting Baryonic Tully-Fisher relation with H1 21 centimeter interferometric observations. So she's online. So Prerana, please share your screen. Have you unshared it? Narendra will unshare it. Okay.
Hello, am I audible?
Yeah.
Okay.
Yeah. Background noise is there, so.
Is it so? Is it clear now?
No, still it is noisy.
Okay, just. Okay. Let me just switch off the fan.
Yeah, you might have some fan or something.
Now is it fine?
Yeah, it's better.
Okay. I will share my screen. It's saying that host disable participant screen sharing. I think I'm not a host.
Co-host
Oh, actually, I got disconnected middle way and then rejoined. That's why maybe I lost this permission.
Yeah, just wait for a minute. They are trying to resolve the issue. Maybe we have your audio, so have some background in case you want to start.
Okay.
Yeah, any other speaker is ready? Let us say next Sandeep Kumar Kataria. If you are able to share your screen as a co-host. Sandeep? Subham Ghosh? Any other speaker online who can sort of, yeah, now someone is, okay, Sandeep Kataria. So Prerana, let's work on your issue. Meanwhile, we can have talk from Sandeep Kumar Kataria, who would be talking from effect of dark matter inner angular momentum on box peanut X-shaped bulges in bar-shaped spiral galaxies. So Sandeep, you have 15 minutes and we will remind you after 10 minutes, and within that next few minutes you have to complete it. Please go ahead, Sandeep. Sandeep? Sandeep, can you hear?
Hello, can you hear me?
Yes.
Can you hear me?
Yeah. Yeah, probably you have shared again. Yes. Make it full screen, please. Yes, go ahead. You have 10 minutes plus 5 minutes. So after 10 minutes, I will remind you. Please go ahead.
Okay, thank you. So first of all, I would like to thank organizer for giving me opportunity to talk about my work here. So I will be talking about the effect of inner and X-shaped bulges, which are usually found in barred spiral galaxies. And this work has been done with the collaboration with Juntaishin and Moshimi at IA. So this is the brief overview of my talk, where I will briefly introduce and then why I'm motivated to work to see the effect of inner halo angular momentum, which is surrounding this disk. And we generate some, we do n-body experiments where we generate a disk model, and then we evolve. And then I will later on discuss the effect of halo spin on this BPX bulges shapes and their line profiles and buckling, etc. And then I will summarize. Introduction of BPX bulges. So this is the one of the Kobe image on the top side of Milky Way central region, where you can see there's a clearly visible. But when you see the WISE image of Milky Way, then you can see there is a clear X shape in the central region. When you zoom in, then you can clearly see that there are star particles which are having X shape kind of distribution. So yeah, so and this is about our Milky Way galaxy, and these type of shapes are found in many other other galaxies also. So usually these box peanut shaped bulges are thought to be result of the secular evolution of barred galaxies, and we see that in our current nearby universe, the 1/3 galaxies are having these shapes, and these bulges are thought to be produced. These bulges are produced to be thought to be produced by the buckling of bar, which happens just after the bar forms in the disk. or it has been shown to be due to the orbital trapping in the 2:1 vertical resonances, which can be at fast pace and the slow pace. And these details are discussed in this paper. And in some of the galaxies, like you see in the right hand side NGC 4314 KS image, when you see face on map, then you see some bar lines kind of structure, which is also shown to be due to this due to the buckling of bar in simulations. And you can see that it can produce nicely bar lines in the vertical shape, sorry, face on shape. And when you see in the edge on map, then you can see nice X structure. So these are correlated with each other. Now moving on to the motivation behind checking the effect of inner angular momentum. So the right-hand plot shows the distribution of angular momentum in cosmological simulations. It outlines several simulations done around a decade or so. So you can see that there is an halo angular momentum is peaked at a certain value, which is I think this x-axis is the spin value, which is proportional to the angular momentum of halo, the surrounding dark matter halo. So it peaks around 0.035 number. And so yeah, so we have a different angular momentum of halo, which is distributed over large range. And there has been previously work done which shows like if you have a faster rotating halo by Saha and Nab, that you can trigger bar earlier, and then it can hamper the secular growth also. It has been shown by later work. So this in turn has an effect on the BPX bulges. So, and we have also shown in our previous work where BPX is largely affected by this bar in the disk. So, and there are various ways to vary the spin in the halo. So there is a lot of opportunity to work here. So we wanted to ask the special question: how the inner angular momentum of halo affects the BPX shape of bulges. So whether we can get the clue of the dark matter halo which is surrounding the disk on the imprint on the baryonic component. So for this, we start with the n-body model, and we generate an axisymmetric disk with the Galaxy code, which uses elements of Schwarzschild method to populate a given density distribution. And we take around million particle for disk and halo component. Halo is Hunquist in our model. So the left figure shows the more of the details of our initial conditions, where you see the velocity is shown in the top left, where for individual contribution from the individual contribution from the from the components are shown in this dashed line, which are from disk and halo. And then the surface density is also decrease is a kind of exponential, and then sigma is also decreasing as you radially decreasing. And q parameter is which is the measure of the local instability in the disk. It is greater than 1 at all radii. Now so as we are interested to check the effect of inner angular momentum, so we make 6 model. 5 are having the co-rotating halos with disk, and 1 is the counter rotating with respect to disk. So the main difference is the inner prograde fraction is we are varying, which is we are using the idea of Jean's theorem, which says that if you have a given density distribution and potential, then the solution to the orbits are possible clockwise as well as anti-clockwise. So we are free to vary the fractions in the central region. So that's what we do. We vary the prograde fraction, which increases from lowest spin to the highest spin. And for counter rotating spin, it is the other way around. So you have more of a retrograde orbit in the central region. So as our models are ready, we evolve this model with the gadget code up to 10 gigayear. And then we use this code uses the tree method, which is kind of makes the things faster from log n square to the n log n calculations. And the main key ingredients of this simulations are that you need to conserve angular momentum and energy. So in the right side you can see that disk is evolving, and I have made the disk to be in the static in bar to be in x direction. So here currently it is evolving up to 6 gigahertz, and you can see that there is a vertical thickening of the bar Now it is starting, so you can see that disk is exponential in the edge on, and now it start buckling, and then it shows the vertical strength going on, and then you have a second buckling event, and then it again further decreases, so increases. So this is one of our model, and we evolve all of our model, and then we check the final face on and as well as edge on shape of the bars. So this is the lowest spin model, and this is the highest spin model, and this is the counter rotating model. So you can see that face on shape of the bar is kind of showing a peanut shape as well, and it is pronounced when you have a more halo spin, more rotating halo. And on the other side, you also may be seeing that the thickness of final bar in the XZ cross section is also enhancing as you increasing the spin, which I will show in a more of a plotting manner, because from the eye it is not very clear here, but it's kind of enhancing. And for counter rotating case, you have a ring, which ring kind of structure you can also see, and a nice spiral which are sustaining here. And then to quantify this effect of boxiness in the fashion shape, we plot a line profile along plus 4 kpcy and minus 4 kpy, and then along the axis of the bar, which is passing through z is equal to 0. So these are the line profiles of all the models, and you can see the dip is kind of increasing as you increase the spin of the halo. So basically, it has an effect on the shapes of the bar in face on. Then we also see the effect on these are the time evolution of our models, and these are quite detailed plots. So left one shows the bar strength plot, which is the m is equal to 2 Fourier mode. And you can see that as the halo which is rotating around the disk, if it is rotating faster, then you form bar earlier, which is shown in the previous work also. And then in the circular evolution, we see that our bars are being sustained, and which is, I think, our initial conditions are designed in that way. So we see the secular growth is the bars are sustained in secular evolution. And for the counter rotating case, the bar is forming the late, and it has a consequences on the angular momentum transfer from the disk to halo, which I will show in a later plot. And the middle panel show the buckling event, which we capture as vertical modes in YZ or XZ plane, where you can see this P corresponding to the buckling time scale. And buckling happens earlier as you have a more faster rotating halo. And then you can see also second peak in each color, which corresponding to the second buckling event, which is, I think, more pronounced in our S075 model, which has
Sandeep,
the
10 minutes are over now. So you have
Okay,
a 5
thank you.
maximum.
Yeah, thank you. So basically, your buckling is second buckling is more pronounced in higher spin model, and the time scale is also a bit higher, which is another thing which we found very interesting. And then the rightmost plot shows the box peanut shape, the strength of this box peanut bulge, and which is measured as the root mean square z height of the stars in the disk. And you can see that this is kind of depends upon the spin. If you have a highly spinning rotating halo, then this value is higher for the highly spin cases. And this is also one of the interesting thing we see. Then we also capture the multiple buckling events in sigma z by sigma r plots, which you can see there is a dip in the sigma z by sigma r as the buckling happens, and you see the second peak also more pronounced in S075. So high spin cases have a more chances of multiple buckling. Then we also looked into the pattern speeds of our model. So we see that all the models are initially they are fast, but as they evolve, we find the slow bars, and it is, I think, so it is interesting in the view of lambda CDM and observational tension of this pattern speed in the bar. So our results suggest like these pattern speeds are like bars are slow irrespective of the halo spin. And then coming to this angular momentum exchange between the disk and halo. So this kind of says why we are getting earlier bar for faster rotating halo, because there is a faster angular momentum exchange in the bar formation phase, and which kind of triggers bar formation earlier. But in the secular evolution phase, the trends are reversed. So the angular momentum exchange is kind of being hampered, and the slowly rotating halo is getting more angular momentum. So that's why we are getting around bars having similar pattern speeds, and then it also have a same strength in the secular evolution. And this black curve shows the counter rotating halo, which has gained a more angular momentum, as we kind of expect. The angular momentum transport is expected to be more in counter rotating cases, because there is a lot of scope of exchanging angular momentum. So these are my final comments and take home messages for the talk. So we show that inner angular momentum of the halo is very crucial to bar formation and its secular evolution. And this evolved face-on shape of bar changes from rectangular to the pronounced spinner shape as the halo spin increases. And in Ajon, BPX shape is more pronounced when you have a high spinning halo or more angular momentum in the central region. And tendency to have second buckling is increases as you have a highly spinning rotating halo in the surrounding region. And the time period of the second buckling is much higher in our cases, which is of the order of giga year, and which is much larger than the first buckling, which usually happen of the few hundreds of the mega year. And we see that bars are slow, and it doesn't depend upon the inner angular momentum. So the final bar are slow, basically. So thank you.
Yeah, thank you. Thank you, Sandeep. Time for one question. Online participants, if you have any. Please drop them among the audience. Oh. Yes, Sandeep, you have a question here from audience.
Hi. Is it audible?
Yeah.
Okay. So this is really good work, and I think many people are aware of this. However, there is another parallel model where a merger has been thought in producing this X-shape structure in galaxies. Any comment on that? I think there is a simulations by Hernquist, very old paper. They also says that if another small galaxy falls in a particular orbit, they also can produce X-shape structure. How to disentangle between these two models?
Okay, yeah, that's a good question. So usually these X shapes are produced by the bar kind of feature. And yeah, if you have any small galaxies which are merging into the larger host, then it can also provide the perturbation which can make bar kind of modes. And if you have a bar kind of modes, then you can, I think, produce this X-shaped structure, because bar usually, as we know that in many simulations as well as previous work shows, that if you have a bar, then it will buckle after some time. It mostly happens all the time only. So in that way you can explain, I think.
Yeah, that's okay, but
Yeah, I think you also please continue discussing over chat.
yeah, that's
also lack of time, Sandeep, again, and we have to make sure that the time is maintained. So again, we will come back to Prerana if at all she is ready. Please unmute
Yes.
and share. Yes, Prerana,
Yes,
are you ready?
Yeah, I'm ready.
Yeah. So the previous speaker who had some technical difficulties, so we will go to her again. Revisiting Baryonic Tully-Fisher relation with the H1 21 centimeter interferometric observations.
So my screen is visible, right?
Yes.
So the
Yes.
slides
Yeah.
are visible.
Yeah.
Okay.
Please go ahead.
Yeah.
Please
So
make sure that the time is maintained.
yeah, sure.
Yeah.
Hi everyone. Good afternoon. So today I'm talking about the so-called Baryonic Tully-Fisher relation, but with the H1 21 centimeter interferometric observation. Okay. In a seminal paper, Tully and Fisher in 1977 discovered a tight correlation between the luminosity of the galaxy and the width of the global H1 profile. Now, these both luminosity and the H1 line widths are proxies for more fundamental quantities. The luminosity relates to the stellar mass of the galaxy, while the H1 line width is an indicator of the circular velocity, which depends on the total mass, that is the baryonic mass and also the dark matter halo mass of the galaxy. This relation is a very important relation as it has been used in extensively in determining the distances, estimation of the Hubble constant, and also for the study of the local galaxy flow, etc. Now, in 2000, this Macau et al. Discovered that this relation breaks down for velocities smaller than 1,000 km/s. What happens in this regime is that this regime is dominated by the gas-rich dwarf galaxies, in which the cold gas mass is comparable to or even sometimes larger than the stellar mass. So they provided that when stellar mass is replaced with the total baryonic mass, one recovers a single linear relationship over almost 5 decades of M baryonic mass. Okay. Now, to establish this relationship, there are different forms of the velocities have been used in the literature. So, for example, this WP50 and WM50 and WP50 are the width of the global H1 spectra, so which indicates the rotation velocity at the edge of the galaxies. And this is defined as the 50% of the mean flux, this blue line, and P20 is the 20% of the peak flux, which is this red line. And also sometimes it is given by V flat, which is the velocity at the flat part of the rotation curve, and V max is the maximum velocity, which comes from the rotation curve. But using these different kinds of the velocity keeps different slopes and intercepts in the Baryonic Tully-Fisher relation, and thus we get the different scatters in the Baryonic Tully-Fisher relations, and it's all right. So now the point is that in the previous studies are mostly based on the single disk observation. Whenever we look at this plot, the global H1 spectra can be obtained from the single disk observation. But Lilly et al. On 2019, they studied with the Spitzer dataset and with the spark rotation curve, which contains near about 175 of the galaxies. They showed that this V flat gives the tightest Tully-Fisher relation. So these plots are from their paper. This one is for V flat. This one is the widths at WP20 and WP50. Here you can see that the V flat is giving the tightest Tully-Fisher relation. And also there is another aspect that for most of the cases, when the width of the spectra is corrected for the inclination, the optical inclination has been used. But that may be a matter of concern because the optical inclination is defined from the isophores of the optical observation, but it can be different from if we define the inclination from the H1 observation. So later in this talk, we will be exploring about this in details. So for our study, we have selected, we had 11 sources from the GMRT archive atomic gas survey, Garcia, where we have we have presented 515 sources observed in the GMRT L band with channel resolution less than 33 kilohertz, so that they have been observed in the spectral line mode, and ensures that their kinematical modeling can be done satisfactorily. As a pilot survey, we have analyzed 11 sources of this as a part of the survey, and we intend to do it for all of the sources and make the result public in a phased manner. So here is some distribution of these sources. As you can see, this is the optical diameter, beam and magnitude, and this one is H1 mass versus this velocity width, which can be called the gas Tully-Fisher relation. And so we take the 11 sources from the Garcia survey, and again we observed 15 sources as a part of the MassQ project, which intend to study the quenching stages of the star formation quenching of the galaxies, and it is in collaboration with the H. Khalifa group, and where these Khalifa group observed have their KPC resolved stellar maps, and the H group has their follow-up CO line observation for some of the Khalifa galaxies. Now, with this, we have now 26 sources, and 9 out of the 11 Garcia sources have their SDSS data available. And we need the SDSS data because we wanted to make the photometry to find out the star velocity contribution for the total velocity. And out of the 15 sources, we have found, after doing the analysis, we found that for 11 sources, we have found the line undoubtedly. And among these 11 sources, for 10, we got the successful rotation curve fitting. For one source, there is a big central H1 hole, even in the lowest resolution of the cube, and thus the rotation curve would have defeated. That make our total number of sources for this study is equals to 18. Okay, so these are some data products. You can see the moment maps over here, and we get the global H1 spectra from the integrated from the cube, and also the rotation curve from the fitting. Here from the 3D kinematrical modeling. Okay, now this H1 spectra gives us the line flux, the width of the spectra, and from the line flux, we can compute the H1 mass. And from the rotation curve, we get this value V flat, and also we will be using this rotation curve for the mass modeling. All right. Now, as I have mentioned earlier, that Lilly et al. Found that the V flat gives the tightest Baryonic Tully-Fisher relation. But there is a difference in determining V flat by doing the 2D kinematical modeling of the velocity data field and doing the 3D kinematical modeling from the data cube. So what Lilly et al. Did is they took the data from the literature, and mostly all the data, interferometric data, they use 2D kinematical modeling and find out V flat from the rotation curve. But there is a key difference between doing the 3D modeling and the 2D modeling, because in the 2D modeling, there can be, the result can be affected by the beam smearing, or there can be the projection effect. So as a study to, these people, the Campus et al. Studied the difference between the 2D and the 3D fitting with the 25 galaxies from the LV sample, and they showed over here that there is a factor of this plot is the, this section is the difference of the 2D done by the Rotker and this fit, and this one is the 2D fitting minus the 3D fitting, which is obtained by their own pipeline, which is FAT, the tilted ring, fully automated tilted ring fitting code. And here you can see there is offset of around 15 degrees in their results in the inclination, and the inclination offsets results in the velocity offsets, which is here you can see it is around 4, and this is channels, and their channel width is 4 km per second, which results in almost 16 km per second offset in the observed V rotation of the galaxies in the 2D and 3D fitting. Okay, so this proves the importance of doing this study with the 3D kinematical data. Now, there are two pipelines available in the market, which helps us to study this 3D kinematical modeling. One is FAT and one is B-Barlow. So for nearly half of the sample, 11 Khalifa Garcia sample, we studied it with both the pipeline and compared the result, and we see that FAT gives more reliable results because first of all, FAT can fit reliably between 20 degree to 90 degree of the inclination angle, while the B-Barlow can fit reliably if the inclination angle is between 45 degree to 75 degree. And FAT,
you have 5 minutes to go.
Oh, okay, yeah, sure. Okay, so we are going with this. Now you see that we compare the inclinations and the different velocity forms. Here you see that I flat versus the I optical, and at the lower inclinations, we see that they are deviating too much. And here we compare the V flat with the width of the spectra, which is corrected with the optical inclinations. And here the width is corrected for the H1 inclination. And you clearly see that this gives more tighter relation compared to this, which proves that we should use the kinematic inclination to correct the width of the spectra. Now we are going to the mass modeling. For the mass modeling, we had the SDSS R-band data. With the R-band data, we fitted the multi-Gaussian expansion fitted to the luminosity and find out the luminosity. And this luminosity will, will taking the constant light to mass to light ratio as a prior. We solved the Jeans anisotropic equation via JAM model to find the V star contribution. And we consider the V halo as an NFW profile and took the prior as these M200 and concentration parameter C. And for now, we have ignored this V gas contribution, and V total is our data that comes from the H1 rotation curve. So we run the MCMC simulations with our free parameters in mass to light ratio M200 and C. So here are some results from the simulation run. We can see that the ML comes right around the 5, which is almost equal with the SDSS R-band mass to light ratio, which is 5. And here are the results of the mass modeling. You can see that at the larger end, this blue line is the halo mass profile, halo velocity dominates, and the stellar mass contribution, which is this yellow light, it gets reduced. Okay, now what happens is we compare the distances bound by both the methods. So first of all, we took the distance from the literature and find out the mass of the H1. And from the MCMC code, we got the light to mass ratio. And from the MGE code, we got the total light and find out the baryonic mass. And then here, what we have previously had this WV flat and the WP20 and M50. Then we took the Tully-Fisher relation best known from the literature, which is from Lilly et al., and find out the baryonic mass. Now, from this baryonic mass, we find out the distances of the, and we compared the distances with what we have taken from the literature. So here are the, this y-axis is the fraction of the differences and x-axis is the Tully-Fisher distance found. So here, look at this third plot. This says that there is a around 20% of the offset with the, difference between the Tully-Fisher relation found and the difference of the literature, distance found from the literature. So it tells us that the importance of doing this study with the help of the interferometric observation, H1 observation, and doing the kinematical modeling and using the V flat for the establishing the Tully-Fisher relation. Okay, so as a future aspect, we will be doing this study with more rigorously and to get a more accurate result by incorporating the H alpha rotation curve values from our collaborators, from the Aegis collaborator, which have these, you can see for comparing these two. Here is, we have used only the H1 data, here H alpha data and H1 data has combined. And also we are planning to use the Spitzer 3.6 micron data where the mass to light ratio is most consistent, and also incorporating the molecular hydrogen mass from the CO data and the mass to light ratio varied with the distances. So that is our future aspects. I sincerely thank my collaborators, Nirupanda, Narendra, and Veselina, and all the audience who are thanks for listening to this talk. Yeah, thank you.
Yeah, thanks, Prerana. Time for one or two questions. Online participants, please. Do you have any question? Online participants? Oh, among the audience? Yes, please.
Yes, yes, yeah.
Yeah, we have one from here among the audience. Participant also.
Hello, Prerana. Can you hear me?
Yes, yes, yes.
So I have a question regarding this Tully-Fisher relation. So is there any effect of the presence of the bulge on this relation?
Yeah, that can be. And as we are doing the mass modeling, and if there is any, we hope we can found it by doing this mass modeling. But right now I cannot say anything about it. Yeah.
Okay.
Okay, online participant, you have a question?
Oh, so nice talk, Prerana.
Thank you.
Yeah, just one small clarification. Maybe I'm confusing something. You're calling it Baryonic Tully-Fisher relation.
Yes.
Why do you call it? Why do you give it that name?
Oh, actually, this I mean the main relation was established by Tully-Fisher with L, that is the luminosity coming from the optical observation. But later, McGow et al. In 2000 find out that more tighter correlation can be found if we replace this L with the baryonic mass. I mean, L comes from the stellar mass, but baryonic mass contributes the stellar mass and also the gas mass. So yes, that's after this 2000, people called it this Baryonic Tully-Fisher relation.
Okay, I see. So it's you are thinking of the so not just stars. Okay, thank you.
Yeah, thank you.
Yeah, thanks, Prerana, once again for your talk. And to
you,
maintain the
everyone.
time, now we have another in-person speaker. There is Sonali Sachdeva. So Dr. Sonali would be talking about stardust geometry as a main determinant of dust attenuation in galaxies, nearby galaxies. Yeah. So Sonali, you have 15 minutes. Summary. Okay. Yeah, please go ahead.
Okay, hi, I'm Sonali. I'm a postdoctoral fellow at Raman Research Institute, and I would like to tell you about the work that we have done lately. This is with Professor Prerana Nath at the same institute, and so the main thing is that how the properties of the dust inside galaxies is related with how dust is distributed inside a galaxy. So I would tell you why that is important, why we have been focusing on dust for the past few months, and what is the significance of the result. How do I move to the next slide? Okay, so dust in galaxies is as ubiquitous as the stars, as the dark matter, as is the gas. And I'll tell you why dust is one of the most important components, as are the others. So I think that can be easily understood just from this graph. Dust in galaxies, it reprocesses more than half of the stellar light. So the light that is coming from the star. So you can see here that this is the stellar emission. This is from Bulges. This is from this. So the light that was supposed to be here in optical, in UV, that has got scattered, that has got absorbed, and that is getting re-emitted in this region. This is the far IR, middle IR region. So for example, Milky Way would have been doubly bright in the optical if there was no dust. So so all this emission is due to the reprocessing of the stellar light by the dust in galaxies. So here you can see that more star forming a galaxy is, more is the emission in its middle and far IR region. So there can be two reasons for it, and it could be that both of the reasons are contributing. One is that if the galaxy is more star forming, that means it has more gas, it has more dust. So then definitely you would have more emission in middle and far IR, and also dust would have more rays to deal with, I mean more photons to deal with, because there's more star formation happening. So more UV, more optical radiation. So you can see that more is the emission in the optical, in the UV, more is the star formation, more is the emission in the middle and infrared part of the spectrum for the galaxy. So this is the SED spectral energy distribution of the galaxy. Right. So the interesting thing is that dust is reprocessing more than half of galaxy stellar light, but it is a minuscule component in terms of mass. So we all know that the baryonic mass is 1/6 of galaxy's total mass because of this dark matter. And if you consider only the baryonic mass, then 1/6 is in interstellar medium. And if you consider the interstellar medium, then 99% of that mass is gas and only 1% is dust. So in terms of mass, you can of course neglect it, but when you see the properties, when you see, I'll tell you will understand the importance even more in the coming slides. So where is this dust getting formed? So what you need is a metal-rich medium. You don't want it to be too hot. These kind of conditions, these kind of conditions are created around supernovae. But then the challenge is that that dust might get destroyed with the shock waves that are produced with it. Then the asymptotic giant branch of the stars that provides that medium. Then they are also supposed to be forming around supermassive black holes, and then there are debates around it. And then where does it get destroyed is this when there are UV radiations from the stars, and also it gets absorbed. I mean, it gets used when there are star formations. So stars absorb that dust. So they are the part of molecular clouds. They help in the coagulation and the formation of molecular clouds to begin with, and then star formation. So what I want to convey to you through this slide is that how dust is totally related with the star formation history of a galaxy and to the future star formation of a galaxy. So you can understand how galaxies have formed and evolved if you are able to trace how dust has evolved in galaxies. And how do you trace that? How do you understand the presence of dust? That is through dust attenuation curves. So what this is giving is this A lambda, this is the attenuation. So this is, or you can say optical depth. So this is the optical depth as a function of wavelength. So you can see that most of the attenuation happens in ultraviolet. So see, here it is highest. Here these curves are highest. And then the attenuation drops as the wavelength increases. So at optical, it will be lesser. There's also a bump. And then, and by the time it's infrared basically, if infrared is there, it would just pass through. Dust, because the size of the dust is like 0.01 to 1 micron. I mean, it is 2 orders of magnitude smaller than the dust you see around. So it is able to act on only very small wavelengths. So here it is acting. So attenuation curves basically are highest in UV. They are there in optical, and they are almost zero in post near IR. But dust emits in, so this is the attenuation curve. Now, if you see the SED of a galaxy, then you will see FIR and MIR emission, which will be from dust. So this is not the SED of a galaxy, this is the attenuation curve, right? Okay. So yeah, one of the very important things why we want to understand and how understanding of dust, understanding of attenuation curves throughout redshift is important if we want to understand the formation, evolution of galaxies, the fall of stars. So what has happened is, so this is the number of stars getting formed per unit co-moving volume with redshift. Now you can see at redshift 2, the star formation that was happening inside galaxies was almost 5 times what is happening now. So there has been a huge fall. This is called a quenching problem. This is called, this problem is given many names and dealt with in many ways. So why has it decreased? There could be 2 reasons. One is that the fuel has gone down. So means the gas and the dust inside the galaxies has reduced, or the star formation efficiency went down. So the fuel is there, but you are but you're not able to transform it into stars. So what has been the most dominant contributing factor? So that you need to, if you need to understand, then you need to know the attenuation curves of galaxies and how they behave for different galaxies over the redshifts. Okay. So how these, this is very interesting, that how these attenuation curves have been getting estimated and how progress has been made over the years with newer observations. So with newer observations and more advanced softwares. So first, what was done is that you will stack galaxies according to their Balmer decrement. Okay, but what was happening was that you were giving same attenuation curve to a lot of galaxies that were clubbed together, but we wanted individual attenuation curves. So what is SED fitting is that first you create yourself, you model dust-free attenuation, dust-free SEDs, dust-free spectral energy distribution for galaxies. Then you apply a dust attenuation curve, and then you see, then you match it with the observed spectra. Observed spectra, there are billions of observed spectra from various galaxies, and then you are able to get the parameters. But what is happening here is that you are assuming a dust attenuation curve. But now if you have, but now what has happened is we have observations in the far IR. So how do you go back? So okay, so because you have observations in the far IR, you are able to put a constraint on the total dust emission. So that has improved the estimation of. So now you can estimate dust attenuation parameters in the fitting. So okay, so what has happened is that now you have dust attenuation parameters for a lot of galaxies, for millions of galaxies, and so there are these small patches which would have a lot of observations from ultraviolet to infrared. So for example, there is one such patch, type 82. It has been observed by multiple surveys. So then what happens is that different groups do work on that, and so for these kind of galaxies, this is the sample that we have chosen. We have dust attenuation parameters also. We have structural parameters also, stellar parameter measurements also. So now what we can do is that we can see if the dust attenuation parameters, if the properties of dust are related to the structure or are related to the star formation parameters in any way. So you see why that is important. If you see the local galaxies, so here this is local galaxies, you can see that there are ellipticals and there are spirals, and you want to know how they have formed. For example, in ellipticals, it is assumed that they were major mergers and they are the product of that. But for spirals, there could have been minor mergers and there could have been accretion, etc. But if you want to understand that, if you are able to correlate what is the correlation of structure with the attenuation properties, then you can say a great deal about what has gone into, if the dust properties are different, how similar they are. You will be able to say what have been the dominant physical processes that have contributed to the formation of these galaxies. So what we did is that we had this sample, a huge sample of 17,000 galaxies. We have just separated them into, if they have a dominant spheroidal component. Spheroidal is basically stars having a huge velocity dispersion, and that's how they are countering gravity. Or they have a dominant disk component where most of the stars are rotating in a disk-like structure. And so when we divide galaxies in that manner, we see that their slopes, their UV to optical, their normalized slopes are absolutely different. They have distinct values of the normalized slope. So what is happening is, so what is the interpretation of this is, see, so disks, if they have a shallower slope, they have a shallower value of RF UV than spheroids. So shallower means that as much as the attenuation in UV, that much is the attenuation in optical. But spheroids have steeper slopes. What that means is that the attenuation in UV is much more than that in optical. So what is happening is that for spheroids, the stars in the birth cloud. So when stars form, there's a birth cloud. Only those stars are getting attenuated. But rest of the stars are not getting attenuated. But this they have lot of birth clouds, and they have lot of dense interstellar medium dust. So they are getting attenuated throughout, not just the UV, but optical also. So you can see it in terms of, if we divide galaxies into star forming and passive, you can see that again they have distinct values of the slope. So passive and spheroid galaxies are behaving in a similar manner. So what this tells you is that how dust is distributed within a galaxy, that would determine how the attenuation will be. So if dust is mainly within the clouds, within the birth clouds, or if dust is diffused in the interstellar medium, how dust is distributed within a galaxy will determine how the attenuation will work. So that's why it is different for spheroidals, for disks, for passive galaxies, and for star forming galaxies. Okay, so this is my second last slide. So what this tells you is that the total dust amount is not important. So what you can see is, this E is, this is the inclination. So with inclination, there is no trend. Otherwise, with inclination, there should have been a trend that as the inclination increases, the amount of dust encountered increases. So we should have seen a trend with that, but there is no trend. So that means the total dust amount is not important. Here also, if you see only the black ones, this is the total mass. So with total mass, again, there is no trend. So how much dust is there is not important. It's mainly how that dust is distributed. So yeah, dust is distributed within a galaxy. So attenuation curves, why are they important? Because they are important throughout. If you are working in galaxy formation evolution, you need to know the attenuation curves. They are most important for the computation of stellar parameters, to know the star formation history of a galaxy. They are used in all simulations for modeling, and if you want to know the evolution over cosmic time, and of course to understand quenching. So what we have found is that the curves are shallow for disk dominated and steep for spheroid dominated. Similarly, they are shallow for star forming and steep for passive. So, but there is no trend with total stellar mass. So it is not the amount of stellar mass, but the distribution inside a galaxy. And similarly, no trend with inclination. So it is not the amount of dust, but the distribution inside a galaxy. So distribution of stars, distribution of dust. So it is the star dust geometry that determines the shape of the attenuation curve of a galaxy. Thank you.
Thank you. Thanks, Sonali, for this nice talk on this important issue of dust in galaxies. Since we don't have time, we are not going to ask for questions and so on. So thanks again. And now I'm going to invite the next speaker, Subham Ghosh, who would be talking about.
Yeah, can you hear me?
Yes. So the competition between hydrodynamic instability,
am I audible?
Gravitational instability in the Keplerian disk. So Shubham, since time is less and we are already running out.
Am I audible?
Yes, you are audible, very much audible.
Okay.
May I request you to just try to finish within 10 minutes?
Yeah, I'll try my best. So can you see my screen?
Yes, please make it as a full screen.
Yeah. Okay. Good afternoon, everybody. So through this talk, we're going to study the competition between hydrodynamic instability from noise and magnetorotational instability in the Keplerian accretion disk. This work is done with my supervisor, Bani Brata. So observational evidences say that the accretion disks are turbulent, although the underlying flow is really stable. Mean that if we perturb the flow, a local fluid parcel, what will happen due to the very nature of the Keplerian angular velocity? the perturbation, the infinitesimal perturbation or linear perturbation eventually decay down. Hence, the question arises, what makes the is underlying instability behind the turbulence? So it was 1991 when Malbus and Howley put forward the idea of magnetorotational instability, in short MRI. But it is quite popular, even though there are some sites where MRI ceases or even it does not work. So keeping in mind those sites, and apart from that, in general, there are recent studies which show that it could be the hydrodynamic instability itself, which arises due to the presence of an extra force of stochastic nature, or we can call it noise, which has non-zero mean. In this work, we're going to compare the linear growth rates of these two linear instability. One is magnetorotational and another one is hydrodynamical. Now, the question of interest is that what could be the origin of this extra force? So in the context of accretion physics, it could be interaction between the dust grain and fluid parcel in protoplanetary disk, feedback from outflow jets onto the disk, or even the neglected nonlinear terms when we do the linear analysis, etc. So having setting this background, let us study the linear growth rates. To do so, we should have some background. The background velocity is here, as mentioned, linear, which is the local background velocity of a Keplerian accretion flow. And in our case, the background magnetic field is along the z direction, which is spatially and temporally constant. We chose this to mimic the standard MRI. Now we perturb these backgrounds to study what happens to the perturbations in the presence of extra force and in the presence of rotation, which is intrinsic in case of accretion flow. So our equations are usually not Navier-Stokes equation, but recasted form, as pressure can be eliminated due to the incompressibility of the underlying flow. So our equations are the magnetic or Sommerfeld and square equation in the presence of rotation and the noise with non-zero mean. With this, we consider the perturbations of having this form. As the background is spatially dependent, so perturbations will have form like this, and the frequency of the perturbation, which is in general complex. According to our convention, if the imaginary part of this frequency is positive, then there is instability, and the corresponding modes are unstable modes. Alpha is the wave vector. To mimic the standard MRI, we have chosen the this wave vector along the vertical direction. So having said that, we ultimately obtain dispersion relation of quartic in frequency, where this m is the mean of the noise, u0 is the perturbation x component of the perturbation velocity, q contains the information of rotation. It is called the rotation parameter, which is 1.5 per Keplerian flow, and it is related with the angular frequency as shown here. Now, having said that, this equation one, this master dispersion equation, can be reached to the magnetorotational dispersion relation if we make the noise go away. On the contrary, if we make the magnetic field vanished, then the same equation will reach to the will give us the condition for hydrodynamic instability. So let's study those extreme cases one by one, and we eventually go to the solutions of these four solutions of these equations of this equation. So to study the MRI, we have chosen the noise information to noise go away, and we eventually have this quadratic equation of beta square. And if we plot the unstable modes of these from these equations, then what will happen is the following. Along x-axis, it is the magnetic field. All are in dimensionless unit. Along y-axis, it is the imaginary part of beta, the frequency. And these different colors represents different configuration of the rotation and the wave vector. So what it shows is that if you consider any one case of these configurations, what it shows is the following. as the magnetic field increases, the growth rate increases, reaches the maximum, and then decreases. And eventually there is a window within which there is a positive growth rate, that is positive imaginary beta, that is there is instability, there is MRI. Beyond that magnetic field, there is no growth rate. So for your information or to draw your attention, I would like to draw your attention to this rotation rate, which is equal to the Keplerian rotation rate. That is this black dotted line. Here we see that the growth rate is positive within the magnetic field regime of ranging from minus 0.5 to plus 0.5. That is our case of interest. Please keep in mind that one. And we call this regime as the MRI active regime of magnetic field. The other regime we call this MRI inactive regime of magnetic field. And next case, if we make the magnetic field vanished, then we reach from the master equation one quadratic equation of frequency. And if we solve this, we will have these two roots, among which if we make the noise vanished, then what we obtain is that the usual centrifugal condition for centrifugal instability, that is the Rayleigh criteria. Now if we obtain everything, the rotation and as well as the noise, then what will happen, that we study in through this curve. So along x-axis it is the noise information, and along y-axis it is the growth rate, imaginary part of the growth rate. And then we see that for these configurations there is positive growth rate in for positive m by u naught, that means for positive mean of the noise, as well as for the negative mean of the noise. I would like to draw your attention for this black dotted curve, which I already mentioned for the MRI case. This is our interest, and we see here the growth rate is more than 0.5 in positive and negative side, because here we see for the black curve the maximum growth rate is 0.5, but here in the hydrodynamic case it is more than 0.5. Having said that, let's study the whole equation. So as I mentioned, it has 4 roots, and among the 4 roots, our interest is for the imaginary part of those roots. And the first and fourth solution or 4 roots together will give us the pure hydrodynamic one when we have the magnetic field vanished. The third one will give us the pure MRI mode when the noise is vanished. And second solution gives us the stable mode corresponding to the MRI modes when there is no noise. So now let us start with the MRI counterpart, that is the third solution, as we have some interest in this, and it is already in the community well established. We see that, so in this plot along x-axis it is the noise m by u naught, along y-axis it is the magnetic field strength. And these different contours, this is the contour plot or surface plot. These different contours represents imaginary part of beta, that is the growth rate. What we see is the following: as for a particular m by u naught, as we go along the magnetic field, that is along where the magnetic field increases, as we go along, we see that the growth rate increases, reaches a maximum, and then again decreases. So in MRI, and I would like to draw your attention to the fact that magnetic field range here is the MRI in the regime of MRI active from minus 0.5 to plus 0.5. So in the MRI active regime, if there is noise, there is magnetic field, then we see that the instability is almost controlled by the magnetic field itself. On the contrary, if we increase the magnetic field in this plot, you can see the magnetic field range is increased. There,
10 minutes now.
Yeah, okay. So if we increase the magnetic field, what we see is that in the MRI inactive region of the magnetic field, there it happens to the opposite to the previous case. As the noise is increased, the growth rate increases, and it is almost, the growth rates are almost independent of the magnetic field. So in the MRI inactive region, it is the noise that controls the instability in the system. Now let us study the first solution. So in the first solution, as we see the growth rate, so in the previous 2 solutions, see growth rates are 0.8 and 0.4, but in this case the growth rates are enormous. this is 2 for this MU0. And among all the 4 solutions, it contains the highest growth rates, the first solution, which has no MRI counterpart. And as the noise increases, the growth rate also increases. Now, having said another solution is that second solution, which is almost complementary to the third one, in the sense that here we see as MU0 negative, the growth rate is positive. But in the previous case, I showed that when the MU0 positive, there is positive growth rate. So in the sign, according to the sign of MU0, I'm saying that the second solution is complementary to the third one, and fourth one is the complementary to the first solution. So having said discussed all the solutions, let us conclude that the first solution, which is of purely hydrodynamic origin, it has no MRI counterpart. When both magnetic field as well as noise are retained in the system, then even in the MRI active region of the magnetic field, the growth rate corresponding to the first one, that is purely hydrodynamic one, is larger than that of MRI. And this magnitude depends mostly on the mean of the noise. As the mean increases, the rate increases. On the contrary, in the larger domain of magnetic field where MRI is inactive, it is always the noise that takes over the system. So in summarizing these two conclusions, we can say that even in the MRI active and as well as in the MRI inactive region of magnetic field, it is the noise that dominates over the magnetorotational instability. Hence, the system will be unstable and in turbulence that is arising mostly due to the hydrodynamic instability will dominate over the flow. Thank you.
Yeah, thanks, Subham. Since we are already very late, I would like to skip the questions, and if you have any questions, please continue discussing with Subham. So with this remarks, I would like to thank all the speakers of this session and thank all of you participants in person to be present, and let us have a tea break. And, after that, we will rejoin. Thanks.